For our project, we decided to do the double oscillating steam engine. For the project overview, the main objective of the project was to model an engine based on given dimension drawings, and then make each part, and then put it all together in an assembly, and then remake the dimension drawings so that they're easier to understand and follow the dimensioning rules. For our team dynamics, we didn't meet very often just because we could each do our own parts individually. But we usually met after class or during class to discuss the parts. Our first meeting was where we split up the parts. It was about 50-50. And the meetings after that were just mainly to talk about the report and the presentation. I handled most of the report and the presentation, while Jesus handled the sub-assemblies. So for my parts, I had the base plate, the nameplate that goes on it, the cylinder pedestal, which is where the cylinder rests, the crankshaft, which rotates because of the cylinder motion, the cylinder top cover, which is the lid on the cylinder that keeps the steam in, the flywheel, which would connect to some other mechanism to transfer power from the steam engine, the main bearing, which is where the crankshaft and the cylinder rotated on, the piston rod, which goes up and down due to the piston motion, the nameplate, which has the company name of the steam engine on it, and the port block pedestal, which blocks the port for a steam to go in and out. Jesus handled the upright main frame, which is the two side frames that hold the cylinder in place. He did the main bearing block, so that is the housing for the bearing that I made. Jesus also made the cylinder pivot spindle, which is where the cylinder pivots on. He made the port block nipple, which is where you connect some kind of device to bring steam in and pull steam out. He made the pulley, which connects to the crankshaft to rotate it. He also made the cylinder housing and the cylinder bottom. He made the piston rod gland, which holds the piston rod, and he also made the piston rod end, which connects to the crankshaft and the compression spring. So, for my, biggest subassembly, is the crankshaft. I made 5 out of the 6 parts for this one. The flywheel, and then crankshaft part 1 through 4, and Jesus made the pulley. So the crankshaft connects directly to the cylinder, the piston rod, and this transfers the translational motion of the piston rod into rotational motion, which then can be directed through the shaft and used for some kind of mechanical purpose. For the flywheel, it was mainly just I made a sketch and then extruded it out, or padded it out. The sketch already contained all the holes. It was just easier to make the hole geometry in the sketch instead of using the hole command, since there's so many holes of different sizes. And then I just padded the whole thing out and then pocketed the inner circle. For the 4 crankshaft pieces, they're all pretty much straightforward pieces. Some rectangles with pegs so that each crankshaft piece can connect to each other. And then Jesus made the pulley. For the next subassembly, which is the base, I created the actual base, the bottom part of it. Made the nameplate, the cylinder pedestal, the port block pedestal. Jesus made the cylinder, pivot spindle, compression spring, and port block nipple. So this is just the base that like holds the frame and everything else. The base was pretty easy to make, just a rectangle, padded up, chamfer the sides, used a hole command to put holes in, and then you just shell out the bottom. The nameplate was actually a lot simpler than I expected it to be. I thought doing letters in CATIA would be kind of hard, but it was fairly straightforward. Professor Goodman showed me how to just go in the drawing file and just type out the text and then copy and paste it on the part. So that made things fairly simple. Other than that, the nameplate is just a rectangle with a little divot. For the cylinder pedestal and port block pedestal, those are both symmetric about the y-axis. Not too many commands went into those, just a few rectangles. And Jesus made the rest of the parts for this subassembly.
Hello, my name is Jesus Ferrand, and I'm the second team member for the Muncaster steam engine, and I will be going over the assemblies that I created, starting off with the pillow block assembly. The purpose of this part is to hold the crankshaft. The crankshaft's axle goes through the bearings that you can see on the image to the right. This particular assembly consists of 4 different parts. The main bearing block, which is divided into a top and a bottom part, a pair of screws, of M4x10 screws, and the main bearing, which is split into 2 halves. To constrain this assembly in CATIA, this was simply done by applying a coincidence between the axes of symmetry of the screws and the holes of the main bearing block. Similarly, the bearing was constrained in the same way. To fully constrain them, I applied contact constraints between the appropriate surfaces of the screws and the main bearing block. The pillow block assembly is later reused to make the frame assembly, which has the purpose of holding the crankshaft above the base. This particular assembly consists of the pillow block assembly, 2 M4x10 panhead screws, and a main upright frame. 2 of these assemblies are used to make the steam engine. In CATIA, to fully constrain these parts to form the assembly, again, all I had to do was apply coincidence constraints between the screws and the holes of the pillow block assembly and the holes on the top of the main upright frame. Next is the main frame assembly, which together is also known as the bottom assembly of the entire engine. It consists of the previously shown base assembly and 2 copies of the frame assembly. The base and the 2 frames are joined together by means of screws. These are also M4x10 panhead screws. The same constraint method as the 2 previous assemblies was used to fully constrain this part. This bottom assembly is where the cylinder and the crankshaft go into. The purpose of this entire assembly is to quite literally hold the engine together and provide a support for it. Finally, we have the cylinder assembly, which has the purpose of quite literally containing the steam that delivers the power to the crankshaft. Okay, this assembly fits into the previous bottom assembly by means of the central beam that comes out of the right side of the assembly. This fits into the cylinder pedestal to the right, the large pedestal that you could see previously on the base. To the left, there's also a cylindrical feature that has a hole in it. The spindle, there is a little black spindle that fits into the smaller pedestal, goes through it, and then into the circular feature that you can see to the left. That way, that's how this cylinder assembly is held in place. This allows it to rotate to make the engine's motion possible. This particular assembly consists of 5 different parts. It consists of the main cylinder block, which is by far the largest piece of this assembly. It has several circular features, both internal and external. It has fillets and several holes. It has a total of 8 holes. Now, to fully contain the steam, it needs 2 covers. There's a top and bottom cover. The covers are joined to the cylinder block by means of 8 screws. This time they are M4x6 panhead screws. There's a final fastener on the top, which is a hexagonal nut. It is threaded on the inside and outside. This is where the piston assembly fits into. Conclusion and evaluation. The project was successful, as all parts were sketched with relative ease and quickness. The assemblies were simply put together, as the parts had very well-defined fittings. The hardest aspect of the project was the drafting of the individual parts, as they had many features, both internal and external. Team communication was good. However, as a team, we could have exercised better time management, as a great deal of our project was done nearing the deadline.